All right. Last time we talked about the Boltzmann-Gibbs distribution of money. You understood that if we have a market with n agents, and if the total money in the market is M is the capital M, then it's always possible to talk about the average money per agent, like $10 million divided by 5 companies. So each company approximately has something like $2 million, for example. This average of the money which distributed over the number of agents is called average money, which we show by this, as you see the symbol of average M. And if you remember thermodynamics, the average M is equal to is in analog of the average energy. And in thermodynamics, the average energy is called temperature, average of kinetic energy. Average, the Hamiltonian is by somehow, I mean, the averaging is a statistical averaging. It gives you the temperature. So when you talk about the temperature or money temperature in the financial markets, we are talking about the average of the money which is distributed over the number of the agents, which is n. So this is actually demonstrated, if you remember, some real markets, in some real market, by fitting the data, you can show that the probability of the finding finding of the agent with the money amount of the M is follow the Gibbs distributions. Today we continue our discussion. So we talk about the debt. So when we talk about the debt, means that one of the agents receives some money from the reservoir or from the universal source, which is called here bank, and in somehow this money is increase the total balance of the agent. That makes like it looks like a positive money, but in the same time, meanwhile, the agent also has a debt obligation. So, and somehow, if you look from the backside, it looks like a negative money. So one side the money increases the balance, and the other side money decreases. So by the totally, I want to tell you that taking the debt from the universal reservoir or from the bank doesn't change the conservation of the money law. So you can be sure that even if you take some debt like D from the reservoir, so reservoir, the total money is M. So after these transactions, also the total money remain conserved. But it is a discussions that sometimes the agent can take a debt from the universal reservoir or from the bank, and this money increase it, decrease it, actually make the balance negative for the agents. I mean the company, for example, is started to working with $1 million, and it took the debt from the bank with $5 million. So you see that at the beginning, when he received the money from the bank, the balance of this agent is negative. So such case make a debt for a big debt actually for this agent. The probability distribution of the money, like probability of distribution of energy, with the debt never be stabilized. I mean, if the debt is higher than the initial money in this agent market, so it never can make stable the markets, and the probability distributions can be the Gaussian, and the average of this money, if the debt is very heavy, so average of the money in this market tends to the zero. I mean, it looks like a Gaussian distributions of the money between the number of the agents, and if the graph is be very Gaussian, so then you can say that the average will be 0, because in one side you have some agents in the market which probably they have more money, and in the other side you have agent members which they have less money than the agent in the left. So at the final, you can say that the average money in this market will be 0. So those markets are not very trustable, and they are not very stabilized, actually. I will give you the paper to read later, because you have to read some detail yourself. We cannot, because we are out of the plan. I wanted to go next week to our main problems. Sometimes when the money which is transferred in the market from between two agents is proportional to the initial money of one of the agents. I mean, one agent, we have a market with just two agents, agent 1 and agent 2, and agent 1, for example, all right. So we have, for example, we have a market which is with the two agent A and the agent B. Today, this market has just two parts. There is a transaction, financial transactions between A to B and B to A. So if you take the money, if you consider the money of this M1, and if you consider the money of this M2, then during a transaction of the delta M money between the agent 2 and agent 1, for example, the money for the first one will change to M prime 1, as you know, and M prime 1 will be delta M plus M1. Meanwhile, the amount of the money for the second agent, the right partner, he lost some money, so will be delta M plus M2. But generally speaking, as you see, sigma mi, which I is running from the number of the agents, is equal to the sigma m prime I. That was the conservation of the money in the markets. First principle, like conservation of energy. In many cases, this delta M will be proportional to the M1, for example. Some portion of that, I mean, delta M will be delta M2, for example, if it takes from the M2. It will be something like gamma M2. Gamma is a coefficient like of fractions. Then if you consider the change in the money from the first agent, for example, mi will be the agent 1 will receive this, so will be mi plus gamma the other one. If you call A, for example, the first one is A, okay, 1, for example, agent 1, it will be like that. And the second agent, M prime 2, we lost this money, so will be M2 minus gamma M2. And if you have a gamma M2, gamma is a positive number, is a fraction coefficient, as you see. This could be something between 0 to 1. Of course, the 1, 2 cannot give all its money to the first one. So it's a range between 0 to 1. What I want to tell you is that the probability distributions, which before in the market with equilibrium, it was, you remember, it was some like that. It was a Gibbs Boltzmann gives actually distributions. It was given by exponential E minus mt. M was the amount of the money which you are looking for that, so money among the markets. N was the number of the agents or the partners. Don't use the partners, so the correct word is agents. So partner is also okay, but mainly in social physics. So the T, I told you what is the T. T is the average money which is distributed between the agents. So is if the total money is M and you have N agents, so dividing the total money by number of agents gives you. I want to tell you that when the transaction is happened with the proportionality like gamma, then the distribution will be changed. So the distributions of the money will change. How it change, you will see. The distribution of money, instead of to be the Gaussian or to Boltzmann, it will be given by the expressions, which is a little modification of the Boltzmann distributions. PM will be still will have something from the Gibbs distribution. So Gibbs was for the PM will be little different. See, please be active and ask me the questions, because you know I want to be interactive. So ask me a question anytime. That will help you to expect also what they will ask you later. What is the PM? PM is the probability of the finding one of the agents with the money M. So you have so many of agents, many of them have some amount of money. The market number have agent N. Total money, which is in the money like $10 billion, is distributed between all of them, and this is give you the probability. So there is a probability like that. The before the probability was when it was not any proportionality of the giving or proportionality fractions. I mean, the agents were free to give any amount of the money to each others. The graph was like that. Gibbs Boltzmann, yeah, GB. When beta was 0. So beta was 0. When beta 0, this is the graph for beta 0, as you see. Okay. When you have these conditions, when the market is out of the somehow is out of the Gibbs distributions, then we call it multiplicate assets exchange model. Okay. The first one was just a simple exchange when one agent received delta M from the other one, and the other one received give the some delta M to the other one. But the model which the money which will be transferred between the payers is proportional, and it is in the fixed rate. You know, like for example, you take a credit card and you divide the payment in 5 payments. So every month you know how much to pay. Yes, as much as you pay till the first of the month, it will divide it by the 5. If you spend 1,000, it means that you have to clear the 1,000 at least in 5 months with 200 or something like that. So with fixed range. With fixed range, the distribution is not Gibbs. You know, the model will be complicated. The exponential Gibbs will be changed. It is called multiplicated cyst exchange model. And it is little different from that. And this is called gamma distribution. The first one was exponential, and this is called gamma distributions. You know, gamma distribution for real data is show that the red one is the Gibbs. The gamma distributions is like that. It has a peak actually. So gamma distributions will be like that. But there is interesting fact that still with the assessed exchange multiplicated assessed exchange model, with this model multiplicated assessed exchange market, you can call it MOM. In the model which is multiplicated assessed exchange market, the distribution is not Gauss, Gibbs, Boltzmann, Gibbs, but it will be different, and you have a peak here. I mean, in such markets, there is a chance for the markets to reach the maximum. I mean, you can find always one agent with the maximum money here. One of them is the richest one, the other ones. But if you are looking still for the probability of finding the agent with a lot of money, the probability will be very, the probability will be very, very low. But to finding the maximum, you can always have the maximum for here. You can have the maximum, at least here happen. But maximum with which money is not close to the total money of the market, like 10 million. It's like 2 billion, for example, 2 million. You can always find the agent with 2 million. Okay, and the chance to finding the agents with low money is still very low. So you see, those markets are stationary markets. The assessed, multiplicate, exchange markets are the market with the maximum of the probability of finding some money at the maximum probability, with almost zero probability of finding the agent with the maximum money and with minimum money. Maximum, no, infinite money actually. But you know that money never goes to the infinity, yes? Theoretically, this limit never existed. What we have here is that some money, like 10 billion, for example. So $1 billion, for example, is, or something like that, is your maximum money in your market. So taking those limits are very critical. Be careful about the meaning of these limiting situations. All right? Yes.
How much the average of these?
Okay, you can calculate. This is a good question. You can calculate that. This is very good question. So average will be, how you calculate it. Take the integral from 0 to infinity. The license of my mathematical license actually expired just 15th of October. I can no longer do the calculation easily as we did it before with mathematical, okay? But there is a many other software, I think you are familiar with some of them, which they can take integral for you. I will use a software which is almost the same as C. This is called Maximum. Later I will show you how to. Okay, if you want theoretically calculate the average will come like that. You see, integral 0 to infinity m pm dm, integral 0 to infinity pm dm. And pm is the previous slide, pm was that. So you can substitute that just here, yes, and making like this. For that, you need to know what is the gamma. Gamma function is a function from mathematical physics, okay? Appears like that. If you have integral like, I will tell you, like t is a parameter, z minus 1 exponential minus t dt, okay? This is called gamma functions. And it is interesting that the gamma, any parameter will be z minus 1 factorial, okay? It is related to factorial. For example, gamma 1 over 2, you can go and calculate it. Gamma 1 over 2 will be radical p. Okay. So this is, you can calculate the average. Maximum you can also have calculate. To find the maximum, just take a derivative of the probability distribution of the money and set it to 0, so you will get the maximum. Okay, what I expected after today's lecture, first you go and calculate this, average it, but this is the minimum things I want. I want you be familiar with the distributions like the Gauss, Gibbs, Boltzmann, and the distribution of gamma distributions, and you be able to explain to the people, even non-technical persons, about what is this distribution, as now I am talking about. All right. The model which we call about MAM or MAM model, multiple assess exchange model, will be modified, and they make it the model complicated. They say that the money which is exchanged from one partner to the other one not only is proportional to the by this factor of gamma, it could be more complicated. So you can have a model which is called here a generalize of this model. So this is model proposed by Chakraborty in 2000. The model is a generalization of the multiplicated ascent exchange model, and the difference is that here, as you see, m prime I is not lambda m or gamma m. There is some additional terms here. Let's go and study this model a little bit more. Let's to find my whiteboard. All right. So the MAM model, the simple MAM model was that, yes, gamma mi for each one, yes, I equal to 1 or 2. I is 1 or 2. Okay, this is called MAM model, and you see that the distribution of money will be changed. This beta which appear here, one can show that the beta is actually given in the terms of the gamma, and it is given by the ratio between logarithm 2 over logarithm of 1 minus gamma. I told you that the gamma is between 0 to 1, yes? So there is no problem to take the logarithm of something which is between 0 to 1. So if you want to know that what is the gamma change between 0 to 1, if gamma is 0, yeah, so beta, if gamma is 0, logarithm of 1 is 0, so you have 1 over 0 but with minus, so minus infinity. So I can tell you that the diagram will start from here. Then you can say that it will, when gamma is 1, logarithm of 0 is minus infinity, it goes to infinity. So this is the diagram of gamma. Okay, gamma is monotonically increasing if you consider this as a variation for as a parameter of the gamma. This is the simple model, and as I told you, still you have a conservation law of m prime equal to sigma m. All right, let's go to the next one. I told you this is the Chakraborty model, so it's a generalization of MAM model. Okay, in Chakraborty model, let's to write it here, m prime I is not gamma mi, is a little bit different from the gamma mi. Just let me change my pen. Okay, I will come back to it. If you have a question, ask me before I write some things.
Okay.
instead of this, so instead of the writing like this as a gamma mi and the other agent m prime I, for example, this is what is this m prime I gamma mi? This is the money of agent I after he receives some money from the other agent, but the money which he received, this delta m, is proportional to the original money which he have. You remember that m prime, always m prime I was mi plus delta mi, yes? This is all like it. This is the principle of conservation of the money in the market, okay? If there is no corruption in the market, for example. In the first model, my model, we considered m prime I just writing like that. You see that it means that delta m be proportional to mi, yes? If delta m is proportional to mi, then you can write all in terms of gamma mi. The Chakraborty model is a generalization of that. They introduced one more parameter. Instead of that, they introduced another parameter. Instead of the gamma or lambda, they have another parameter. And here you have a total money here. It looks like the change in the money of the agents J, agent J, or you can write M2. You see, it's no worry. You can consider each one. Instead of I and J, you can write 1 and 2. You know how you generalize the model. To generalize the model, you need to consider new interactions, interactions. You know, the gamma mi comes from the MAM principle, multiplicated assessed exchange model. It's supposed that the money which is the money which will be exchanged is proportional to the money which they have. A portion of that, 10%, 5% you give to the other agent. To make the model complicated, you add terms like somebody else, or there is a share budget between all the agents, and not only they can take money from each other, they can take this money from that share packet. You get it? This is the share packet. This is the share packet. And the share packet is not 10% of the total money. It is less than that. For example, you say, we are two agents, we do the exchange with each other, but every month you decide to keep 1% of your money, okay? 1% you and 1% your agent, your partner, okay? And put in this common budget, okay? And when you need, you take some money from that, all right? This is the term which comes here. It's like a loan. It's a loan from the common, without going to the bank, you take a loan from a common packet. Yeah, what's the question?
If we have the third agent, we add 1 minus 2, get.
No, we are not. We are two agents, I and J, okay? Okay? You can have 100 of one. So if you have 100, just write M prime 1, M prime 2, M prime 3, and that's all, okay? But think about the two. We are two agents, I and J, okay? The money which received by the agent I is gamma mi from the other one, and it is also its money increased by gamma mj, and this is the money which comes from this common packet. So this is the agent 1, okay, and this is the agent 2. So they have the regular exchange of the money, or exchange of the money between each other, but there is a third packet here which every month they put some money here, each one, okay? So if they need, they can little loan from their saving account, okay? This is like a common saving account. You got it?
Yes.
Common saving account. So these contributions from the model of Chakraborty will change very, very much. You will guess what it will change. It will guess the distribution. So it will change the distribution. The distribution will be very complicated. The distribution will be very complicated, and actually it is will be something like out of the equilibrium. It looks like your system be out of the equilibrium. So conservation of energy will be broken. You look at, if this is the equations which you have, you can make a sigma from these expressions and see that what happened for the sigma m prime I. M prime I plus m prime j, you guess it will be what? You guess it will be mi plus mj, yes? We don't know. Because this is conservation, conservation of money law.
Which is delta m.
We started by that, We started by the conservation of the money as a principle like conservation of energy. Okay, look, if you back to the model of Chakraborty and just added these two, what is happening here? If you add these two, what's happening is that, let's see, it will be gamma mi plus mj, this is m, plus, you know what I'm doing, I add just two, okay? Gamma mi plus mj is total m, yes? Plus these expressions times m, all right?
Yes.
Plus m, okay, I need to make a bracket here. What is the expressions here? I have a PDF here, so we can use the PDF. No need to. This is the. Okay. M. Okay. You have a fact again. You have m1 plus m2, m1 plus m2. This is m. You have a Kc. 1 minus gamma. I write gamma, but this is lambda actually. Just I don't want to change the same parameter. Plus 1 minus Kc. One minus lambda. What happened here? The things which happen, this expression will be simplified to gamma m plus m times open bracket. Okay, simplify. 1 minus gamma you can factor. Will remain Kc plus 1 minus Kc. So 1. Remain just 1. So here remain 1 minus gamma plus 1. This is will be, if you see, will be m. So, you know, you are in the good point now. If you follow what I say today, you are in the good point. Actually, what you can do is that you can work on the model and propose a new model for money exchange even. Yes? As long as you keep the conservation money low, you can think about what kind of the interactions, I mean, what kind of the exchange I can add it here. You can think about more agents of it, no? Not only two agents, even more agents. Not agent I and agent that, more. But for more, you need more equations. And you need to be careful how to write this term here. All right. So this model is studied before, and you just refer this model as a something which call it generalized MAM, multiple access exchange model, or Chakraborty model. the market can be more complicated. I mean, the distribution of money is not only restricted to what we say, to the Gibbs, Boltzmann, or to the MAM model. It could be also not multiplicated, it could be additive. I mean, the change of in the probability versus the time can be very, very complicated functions. You can have a probability of transfer money between the agent to the other money per unit time. I mean, if the number of agents are more, you can think about each time as one transactions which happen between the agents. There are complicated models which we show that here. In those models, the change in the probability distribution of money versus the time will be something like kernel or integral over the distribution of money at different agents and different things. So this is a very complicated model, and we don't study those models. All right, the distribution of money finished. So if somebody asks you how the money distributed in the market with n agents and the total money m, you can mention these three actually scenario: Gibbs, Boltzmann, the MAM model, and the generalized this MAM model or Chakraborty model. And more models. There are more models. Okay. Now we are talking about the distribution of the wealth. Money and wealth are often used as the same things. You think that if somebody have more money, so it means he's richer. But that's not correct. Actually, in the economy, there is a difference between the wealth and money. And they wanted to talk about here about the difference and about the distribution of that. What is the difference between money and wealth? The wealth, which is symbol W, is equal to the money plus any other property of the agents. For example, the agent doesn't have only money, it has a building of the company, the building. It has some car which is useful to giving the service to the customers. Yes? And it has also some telephone line which they bought and they use that for the communications, and many other, even the people, the human resource is considered as a wealth. Okay, so wealth is money plus something else. If you, in order to estimate the wealth, we have to know that the price of each other property of the agent. If we think that we have one type of the properties and the price of that is P, then the agent I, so we are talking about wealth. You see that the wealth is not equal to money, okay? Wealth is not just the money which you have in the account. It's also what you have something else. So wealth or agent I is equal to the money of the agent I plus the price times the number of the price of property multiplied the times of that. Okay. This S parameter is called the stock. Is like a number of the components you have in your company, like how many branch you have, for example, how many car you have. Yes. For each agent, this is a number. So you can multiply this to the price of that things, and you can find it the wealth. Okay, how to find this? So our question is that what is the distributions of the wealth in the community? Okay, and basically, what is the average of the wealth? How many of the people, or how many of people have the maximum wealth in the company, in the market or society? It is related little to society. So W max, W var, or W average of W, whatever you want, those are the quantity which we are looking for. Again, we start by simplest model. The simplest model which gives you the wealth is more complicated than that what you expected. Actually, again, you have a wealth, and during the time, so you see that the problem here is that the time will enter here. You know why? Why time enter in the distribution of the wealth, but it never appear in the distribution of money?
Because this is during the time it will be changed the price of the stock.
Yes,
Maybe
for example, a building, yeah, well, your building will be old. Yes, so it never will cost $100,000 like 5 years before. It will cost less, maybe sometimes, yes, when it destroyed.
yes.
Or your branch, for example, need repairment or maintenance, which change many things.
Yes.
W will be function of I. So Wi will change to W prime I like usual. W prime I will be again Wi plus delta W. But the problem is exactly this delta. How you can model this delta, this change in the wealth at instead of the time and one instant of time, it is proportional to time. If you back to the equation for wealth, we propose wealth is money plus the price times the number of stocks. So you can see that delta W comes from delta M. It comes also from delta S. How many buildings you lost or give or buy or something else. So delta W actually, the change in the wealth, it comes from the two branch actually. One comes from the delta M and one comes from the delta S, change in the stock. For delta M, you already have the model for that, Gibbs model or gamma model, or the one which we call it MAM or gamma model, because you know it's the gamma function appear here. So this is called sometimes gamma model, and other models also more complicated. Well, delta S also there are some models. So the distribution is model depends to the distribution of it depends to delta S. It depends to the fluctuation of the price, huh? Because delta W is also depends to delta P, the currency change. Yes, with $100,000, 20 years before you can buy a big buildings, but today you cannot buy even a small house. Why? Because the price currency rate changed. It is difficult to make a model, but the model which the people make for the distribution of the wealth is not a real simple differential equation, is a stochastic model. So stochastic differential equations, so it is something like call it stochastic differential equations. The change in the wealth will be stochastic differential equations.
Victor, this is their unit of time.
No, this is the change in the wealth for the agent I, for example. Like before, you expected that the change versus the time becomes like a proportionality of the initial wealth. You remember the model of the distribution of the money in the gamma gamma model or MAM model. Plus, it comes also from the interactions between the other different agents. I mean, the change in the wealth of 1% is not only depends to the how many building he or she have, it also depends to the wealth of the other people. That's the reason that every year the richest person of the world, the name will change. Yes, one time was Bill Gates, for example. One time was the Amazon owner, and next time will be somewhere else, something else, because the distribution of the wealth over the time is not only a function of the money of the one of the agents. It depends to the other ones. If one of those person lost the business or lost some money, then this will be affected. This will affect the wealth of the other ones. This is called stochastic differential equations. If you forget about that, you know what is this. This is a normal differential equation you can solve if you have this. This is called Gaussian random pulse or variable. So it's a Gaussian noise, even sometimes it's called Gaussian noise. You can read that from the data, only from the data of the wealth of the people during years. Gaussian noise, this is called noise. This function ji, this function of ji, they are coefficients which they show the wealth different between the agents. This equation is scale invariant. I mean, this can make model for you, not for the market with 100 agents, even with the market with 200 agents or 2 million agents or any other things. So such equations to be used for any numbers should be scale invariant. Should be a scale invariant. So what is the scale invariant? It means that if you make a quantity change by the number of the agents, the model doesn't change invariant. I mean, if the interaction between the agent Ji change to the n times of the other ones, or n times of the Jij, for example, or if the wealth of the agent be double, for example, Wi is the wealth of the agent I, make a double, or make not double, make z times of the what it was before. This equation remains scale invariant. Working with such equation is difficult, so I want you go and read about Langevin, Einstein. Okay, Langevin, Einstein, stochastic equations, Einstein. In the Langevin-Einstein equation, which are the first order stochastic differential equation, the differential equation which change by the time, and not only that, they are stochastic. They are unpredictable. No, the market is unpredictable. Yes, no one can predict the market 100%. If you go read about the Langevin equations, then the average of the wealth at the time t for one agent will be something like the average of the wealth at initial time when the agent started its business, exponential of a quantity. This quantity is given by the variance. Sorry, it's given by the variance and the average also. So the variance of this, the average of this noise noise functions, eta, plus variance. This is a bracket, it's not average, it's a bracket just. Times t. So it's exponentially again. It's exponentially. The probability distributions for the wealth is not only p as a function of w. It will be p as a function of w and time. It looks like the Gibbs distribution be time dependent. So the probability of the wealth in the one market will be function of the wealth and time all together. And to find that, you cannot make a simple model like Gibbs or the other things. You have to use a model which called Fokker-Planck equations. So this is the equation which you will see here, equation 17. And if you solve these Fokker-Planck equations for stationary solutions, for the case that you consider the probability be time dependent, okay, or the change of the in the time of the probability will be not very much, then you can show that the probability will be Gaussian. But it is very different. You see, the probability will be totally different from the Gibbs or from the other models which we give for the distribution of money. PAW will be, as you see, will be proportional to exponential of, very different. Like there is a J here. J is the average of the interaction terms between the agent. You have a variance here. You have a W here, which is wealth. And you have also W here with the power, with power n. And this n here is given by the average of the interaction and the variance. It is very different from the Boltzmann distributions. All right? So it's non-Gaussian. Even it's not Gaussian. If you think about that, this is not Gaussian. The Gaussian is that, if the distribution is, if distribution is proportional to exponential, for example, minus lambda x square, yes, this is Gaussian. And you can think about that like a Mexican hat, and you can see that the average, for example, here, the average of the x will be 0, and the variance, you can calculate the variance if you have the correct form. Actually, lambda minus 1 here will be 2 sigma square, 2 of the variance x square. All right? But this is very different. Okay. I know the talk today was a little hard for you, but we have to go like that. You learn about the distribution of money, Gibbs, generalization of that MAM model, and you also think about that it could be more complicated. And then we talk about the distribution of wealth, and you see that even in simple case, when you consider the market exchange not very much changed by the time, then the distribution is very different from the Gaussian or whatever. Do you know, I want to tell you about what is the partial P partial T0. What does it mean? I will tell you what does it mean. In quantum physics, we have a stationary state and we have non-stationary state or static, yes? If the wave function is time independent, yes, if the system is time independent, so then the probability finding of the particle position x at time t, this is the probability square, will be equal exactly to probability of the finding of this at position x at the time 0. Yes? It means if you look on the distributions, the distribution at time 0 will be like that. Same, remain the same as the shape will be the same. This is the condition of that. So if you look about the wealth distribution in the society, and you see that the same distributions, for example, the difference of the wealth between Amazon or, I don't know, Apple owner, for example, is 10 billion, for example, dollar. And always you see that the difference between the richest person and the second person remain around 10 billion. Then you can say that the distribution of wealth is time independent. Yes? It doesn't mean that their money doesn't increase or something. Just the profile of the distribution of the richest person remain the same, like what I say in quantum mechanics. So from the Fokker-Planck equation, which is very complicated nonlinear stochastic differential equations, you can get the distributions. But for stationary solutions, when what I say here and you get this, you have a distribution which is very totally different from the distribution of the Boltzmann and Gibbs. If the stochastic groups, if you consider the stochastic groups, then you can almost calculate everything from these distributions. I mean, I want to ask you to go and use the equation 18. Of course, you read first, you have to read about the Langevin-Einstein stochastic equations, and this will be familiar how to calculate the average. Then from this distribution in the stationary solutions, you can get the average. You can find the average easily. And in the second part, for the real data, and this is the interesting that if you think about the real, for example, wealth distribution in UK, because this is billion, so you use about the logarithm scale, then it is interesting that the graph which we should find will be very familiar to the distribution which we propose as the stationary solutions for the Fokker-Planck equations. Okay, the next talk, we will talk about the data and income distributions. We will talk about the income distributions, and then this will be end. So I think after income distributions, we directly goes to the paper of the condensations and studying the crisis. All right,
Victor sent to me this table.